All right, hello to everyone. Welcome to the recursion lectures. So this set of slides, in addition to the pointer set of slides, are probably the hardest topic in this class. Okay, so difficult concept alert again. This is it though. So if you can make it through this lecture, it is smooth sailing, I promise. Okay, so recursion is about finding things inside of themselves. So you got your Russian stacking dolls, this cool picture of, I think it's tea with the woman is holding the same box, and so it goes on forever, right? It's all beautiful. Okay, so let's begin. There's a ton of memes because this is a hard topic, and let's get some examples, okay? Let me try and define this for you. So iteration, what we know about, which is like for loops and things. Like you say things like for into I equals 0, I is less than, I don't know, 42, I plus plus, and then you do stuff, right? That is iteration, right? You're setting your variable called I, it's going until 42, it's being incremented by 1. That is what we have been using to solve repetitive problems, okay? If you need to do the same thing a bunch of times, we're going to use iteration. We're going to use loops, okay? And so while and for are how you solve a problem like this that needs you to do a bunch of things to different numbers, but those things are all similar. So like print 1, print 2, print 3, all that stuff. While and for can do that. It's called iteration. Recursion is very similar. It is looping. It's like going through things. It's doing a bunch of similar things all after each other, but you're not using loops this time, okay? So it's like the body is getting executed in a different way, if that makes any sense at all. So that's all very vague. So let me give you a nice example with factorial. That's one of the easiest ones to first explain, so let's do that. All right, so recursion is when you solve a problem using smaller versions of itself, which is going to be very weird as you start out. I know, it is very weird, but you will get enough practice in this lecture for it to eventually make sense, okay? So you're going to find smaller versions of that same problem inside of itself, and you build up that bigger answer to the original problem using the smaller solution that you were going off and finding, okay? So I'm telling you that factorial can be solved recursively. You can find factorial inside of itself. So let me show you this. Here's 5 factorial, and we know that this equals 5 times 4 times 3 times 2 times 1, right? So I'm telling you that this has a recursive solution. So I want you to find me a smaller factorial inside of 5 factorial, okay? And don't read the rest of the slide yet. All right, see if you can find it. Do you see a smaller factorial inside of 5 factorial? And I think if you stared long enough, or you cheated and looked down to the bottom of the slide, you'll notice that there's 4 factorial staring at you right here. You see that? So in order to solve 5 factorial, you need to solve a smaller version of the same problem. Isn't that crazy? So we call that smaller problem sometimes a sub-problem, okay? So you'll hear me say that a lot. And so you could, if you just had 4 factorial, you could multiply it by 5. So 5 factorial equals 5 times 4 factorial. And that would be the same answer. You see that? That's wonderful. So we found the same problem inside of itself, a smaller version of it. That's very important, okay? It must get smaller. And that is actually how we can solve this problem. We can write code to solve the factorial problem for any number using this fact, okay? Because what's 5 factorial? That equals 5 times 4 factorial. But 4 factorial, remember, that is just 4, let me show you this. 4 factorial equals 4 times 3 times 2 times 1. You can do it again. This is just 3 factorial, so 4 factorial is equal to 4 times 3 factorial, and 3 factorial is equal to 3 times 2 factorial. Isn't that crazy? And 2 factorial is equal to 2 times 1 factorial. It's hard to write a 1 and an exclamation point next to each other. In general, just give me any number, n factorial, here's n factorial equals that same n times n minus 1 factorial. That's the pattern. You see that? Isn't that crazy? That's wonderful. So you just find this smaller subproblem and use it to solve the bigger problem. It's like, okay, go off and find 4 factorial, multiply it by the 5. See that? The problem is, eventually, you need to stop this. You need to find some kind of stopping condition. Okay? You need to find a version of this factorial solving problem that's so small that you can immediately solve it. Okay? And I think if you follow the pattern long enough, you'll get to there. Okay? So this is like 1 factorial, that's 1 times 0 factorial. That actually is defined in math to be 1. 0 factorial, if we follow the rule that we're describing, that equals 0 times negative 1 factorial, obviously. And that'll actually cause the whole thing to be 0, which is not what we want. So we want it to either stop here or here if you're cool, and you want to just use 0 factorial and define it to be 1. I think a good stopping place is getting rid of that. This is a good stopping place right there. 1 factorial, okay? A good stopping place. And we can just say that 1 factorial, let's just define that to be 1, and then this will all stop, okay? We won't have to try anymore, and we can just build that answer back up to 5 factorial, okay? So we can say 1 factorial equals 1, and that's called our base case, okay? This is the base case, okay? And this is called the recursive case. Base case, recursive case. So a lot of new terms, but it should make some sense, I think. This is the case that uses the smaller problems. We say that it's recursive, and this is the base case, which tells us when we can stop. We don't have to find a smaller version of ourselves anymore. We can stop now, okay? So with these 2 rules, you can solve for factorial, can't you? All right, so let me give you this example using just a prettier diagram. Okay, so the base case is, we say that 1 factorial equals 1, and the recursive case is, we say that n factorial equals n times n minus 1 factorial. Gotcha? So let me show you 5 factorial. It's like, okay, that is 5 times 4 factorial. And that 4 factorial is 4 times 3 factorial. That's 3 times 2 factorial, 2 times 1 factorial, and that, we say, is just 1 because it's the base case, okay? So this is our little base case, this is where we stop, and then we build up the answer, saying, okay, yeah, the answer was 1 for 1 factorial. And it's like, okay, I'll multiply my 2 by that. And it gives it back to whoever asked it. It's like, okay, my answer down here is 2. And this one was waiting for the 2 for 2 factorial, and it can multiply it by 3. This is how we can solve the problem. Isn't that cool? So it's 6. And this one multiplies its 4 by that 6 that it got back for 3 factorial. It's like, okay, 24. And this one brings it up, finally up to here, multiplies 5 by the 24 that it got back for 4 factorial, and I think the answer is 120. Okay, so that is how factorial is working. With these 2 cases, that's all you need to solve the problem. Okay? Though you can't like say negative 1 factorial, you kind of have to stop the user before they try that. We don't allow that, but I think you can understand that for most numbers, for all the normal factorial numbers that it's defined for, this will work. All right? So now we're going to code this up, and I'm going to show you how to translate this to code. Like how do you, like what does it mean to do the smaller problem inside of itself? What does that even mean in terms of code? So here we go. We usually, in C++, unless we're writing like a class, in which case it's a method, we solve problems by writing functions, okay? Methods are just fancier functions anyway. So a recursive function then, if we need to solve this problem inside of itself, we need to like get the answer to a smaller subproblem, which is the original one, we call that same function inside of itself, okay? So we have our factorial function, I'll call it fact, int n or something. And inside of it, we're calling fact of n minus 1 to get the n minus 1 factorial. That is weird. but that's what needs to happen. That's what makes it recursive, okay? We're calling ourselves on a smaller version of the same problem, okay? Smaller is very important, so I'll make that italic. All right, so inside of the fact function that we're going to define, you say, okay, in the recursive case, well, you give back n times n minus 1 factorial, yeah? So you just return n times, well, go and solve this problem, please. Fact of n minus 1. And in the base case, if you're in the base case, it's 1. You notice that you're just given 1, and, oh, oops, and then you just return 1. Okay, so that's how you can translate it to code. So that is the idea. Let me code this for you now, okay? And then we'll talk about this stuff down here as well. Are you ready? So, fact.cpp. Oh no. Dun dun dun. That is very odd. Let me restart my Vim. I'll be right back. Okay, now it should work. So I'm going to make a factorial function. It returns back an integer, right? Fact int n, and so fact of n returns n factorial. That's what we would like. And so we have to figure out, let's say we want to solve like fact of 5, so print out 5 factorial. We need to figure out if we're in the base case or the recursive case. So if n is 0, or sorry, if n is 1, we're in the base case, because the factorial of 1 is just 1, return it. Else, or I guess we don't even need an else, but we can do it for fun. We can say, okay, return n times fact of n minus 1, okay? Because that was the recursive answer, because n factorial equals n times n minus 1 factorial. And this is just translating that into code. This is how we say in C++ n minus 1 factorial. We're using our own function inside of itself. Isn't that crazy? And it's going to work. It's totally going to work. And there it goes, 120. It gave back the answer. Isn't that cool? And that is how recursion works. You just think of these recursive cases and base cases, and that is how you can come up with your answer. And of course, you can also make a function that loops. That does like for I equals 0, you go up until n, and you multiply it by itself, things like that. That also works, of course, but now you have options, okay? Sometimes, and you probably don't believe me right now, sometimes the recursive version is easier, actually. Okay, so let me quickly give the iterative version for this for you, just to show you that you can do it 2 different ways now and that you have options. Fact iterative. All right, so if, let's see, int product, because it's a big product, or maybe I can call it res for result, starting it at 1. So I can say, I don't know, for int I equals n, I is greater than or equal to 1, I minus minus, and so we're just multiplying res by I a bunch of times, because it'll go from n to n minus 1 to n minus 2 all the way down to 1. Res equals res times I, and then return res. This should also, in theory, work. Oops. There we go. They both do the same thing, but this one is cool and recursive. It called itself, okay? This is the iterative version. This is the recursive version. Gotcha? So that is all I wanted to say about this slide, and now let me show you how the recursive version is working under the hood, because this is like, okay, yeah, we kind of came up with that, but I don't really understand how it's working just yet. A stack diagram will help you understand. Okay, so let me draw one of those for this. So let's pretend we're about to call fact of 5. All right, so we're like on the stack. We are in main, and then main calls fact of 5, right? And then let's see what happens. Because it's going to check if n is 1, it's not, it's 5 right now. So it'll hit the else case, and it will return n times fact of n minus 1. And in order to give back a real answer, that's an int, it needs to go and first figure out what this answer is, fact of n minus 1. So it needs to go and run that function all over again. So fact of 5 is waiting for fact of 4 to be called and give back the factorial of 4. Okay? And I think you can see similarly, when fact of 4 gets called, it's again not 1, it's going to go to here and return 4 times fact of 3. So it has to go and compute fact of 3 before it can give back its final answer. Fact of 3. And fact of 3 similarly is going to call fact of 2, and fact of 2 will finally call fact of 1. And this is where the magic happens. So notice that fact of 5 factorial, it hasn't finished its answer, because it needs to return back its answer to main so main can finally print 5 factorial. That has not happened yet. Fact of 5 is waiting on fact of 4, who's waiting on fact of 3, all the way down to fact of 1. They need those answers back. Well, fact of 1 is about to return. Fact of 1 will return 1 here, and that makes the stack, we say it unwinds, because it gives back 1 to fact of 2, who was waiting right here to do 2 times fact of 1. It got its answer back, so it can multiply its 2 and give back the final answer. So fact of 2 is now going to return to fact of 3 its answer 2 times fact of 1, which is 1, 2. Fact of 3 is going to return back 3 times fact of 2, which gave back 2. So it can return back the 6. Fact of 4 is going to return back to whoever called it, which was fact of 5, its answer, which is 4 times fact of 4, and we know that's 6 now. Sorry, 4 times fact of 3, which we know is 6. So that's 24. And then fact of 5 can finally multiply its 5 by fact of 4 because it has that answer back now. Fact of 4 gave it to him. So now we have 120, who goes back to main. All these guys go away. We're back in main, and main can finally print to the screen 120. That is what happened. Okay? You see how they were all waiting on the other, the smaller call to work? That is the beauty of it. And so that was interesting, right? And you might think that it's probably very difficult to come up with how to solve for factorial, how to discover this base case and recursive case. So how do you, why do you know you can do this a lot of the time? Why does that work? Let me show that to you. So let's pretend that we're solving some generic problem, call it P, and this P could be anything, could be factorial, doesn't have to be. What recursion is doing is it's saying that, okay, I have a base case and a recursive case. So in the base case, I know how to solve the smallest version of the problem. I know how to solve P of 0, okay? That's what the base case does. And the recursive case, I'm going to write it like this. What the recursive case is doing is it's saying that if I had the solution on the left side of the arrow, if I have the solution to one smaller subproblem, I can build, using that, the answer to a one bigger problem. Okay? That is the two things that you need for recursion to happen. And this is the beauty of it. This is going to allow you to solve any problem size for P of 0, P of 1, P of 2, all the way on forever, because you can start at the base case. And then you can use this recursive rule, saying that, okay, if only I knew the one smaller answer, I can make the next bigger answer. Okay? So from P of 0, the one that you know you have, you can make P of 1 using the recursive rule. Plug K in being 0. Plug K in being 1 now, because I know I have P of 1. I can use that to make P of 2. Okay? So this is how recursion is working backwards, I guess. You can think of it getting to the bottom, which it knows how to solve, and then using the one smaller subproblem to make the next bigger one, the next bigger solution, let's say. And the beauty of recursion is, the way that it will eventually make sense, I hope, the way I want you to think about it is, in the recursive case, don't worry about how this is getting the smaller answer, okay? Just assume that it's going to be correct, okay? Assume that when you make the recursive call to the smaller subproblem, you get to assume right here that this is going to be correct, okay? You get to assume that fact of n minus 1 will correctly give back n minus 1 factorial. Okay? And the secret is, it will, as long as you build up the answer correctly. Okay? And this sounds like magic. I get to assume that this works just fine without thinking about it anymore. That is a weird thing, okay? But it really is right. Because eventually, notice how I was drawing this stack diagram before, eventually it's going to get down to the base case and start building up the solution. It will find an answer, and then it can use this rule forever until the end of time. Okay, so maybe like when you called P of 5 for factorial, it was waiting on P of 4. You think of it this way, in this opposite way, which was waiting on P of 3. And you get to assume that you're eventually going to get this answer because you will eventually hit the base case. And that will be able to be built up into the final answer. Okay, you get to assume that the smaller call will work. All right, that's how I want you to think. I'm going to give you some more examples to prove that. It is a weird little state of mind, I know. Okay, so let's see here. Let's do POW. POW stands for power. Okay, so this is going to compute, this example is going to compute x to the power of y. Okay, so let's try and solve this problem. Okay, so let's pretend we had, like, I don't know, 2 to the 4. Okay, I am claiming that this is a recursive problem, taking a number to a power of another number. Because, look what happens when I expand this. This is 2 times 2 times 2 times 2 times 2. Can you find me a smaller power computation inside of this one? Take a second to see if you can. Similar to factorial, do you see it? It's 2 to the 3. Ooh, that's nice. So it seems that this might work. So in like 2 to the 3, that's 2 times 2 times 2. Can you find the smaller power computation there? Yeah, there's a 2 squared. Oh man. So it seems like m to the n, if you will allow me to use variables, that's equal to, this is the m, it's equal to m times, well, m to the n minus 1. You see that? That is a smaller power computation inside of a power computation. All right, so that's the recursive case. Rec case, let's say. That's the idea. And then the answer is, when do you stop? Like, okay, that 2 squared is 2 squared, that's 2 times 2 to the 1. 2 to the 1 is 2 times 2 to the 0. 2 to the 0 is 2 times 2 to the negative 1? Technically, yes, but I think a good stopping place is right here. You just say anything to the 0th power is 1, and then you can build up your answer from that. Okay, so the base case, a good one is, m to the 0. That's always equal to 1, no matter the m. Okay, so that's your base case. You don't have to do any other work, it's just the answer is 1 when the exponent is 0. Okay, so yeah, just think of your base case as something that stops the computation. And yeah, the recursive case, again, it's doing a smaller power computation. And you get to assume that this is going to give you the right answer, because eventually you'll hit the base case and it will. And it will build up the final answer correctly, the bigger answer to m to the power of n from this smaller solution. Okay, so let's program this. We can do it. Are you ready? And then I'll show you a stack diagram again. pow.cpp. So, here we go. Pow takes two numbers, m and n, and it returns m to the power of n, yeah? So it gives back an int if they were both ints. Technically, the second one can be a double, I think. or no, sorry, the first one can be a double. But these powers have to be whole numbers, okay? Integers. So that will work, and then in that case it will return a double. So technically I could say something like 2.5 if I wanted to the power of 4. Okay, so base case, recursive case. If n is 0, base case. Anything to the 0 power is 1, so we give back 1. That's the answer of any m to the 0 power. Okay? Else, recursive case. Well, whatever the answer is, m to the power of n, well, it's just m times m to the power of n minus 1. Okay? Oops. That is what we discovered. So return m times pow m n minus 1. Okay? So something's getting smaller, the n minus 1, that's getting smaller, but m's staying the same. Okay? As long as something gets smaller, this will eventually work. All right? So let's see if this does. Hey, and it's 16, that is correct. Okay. So let me show you why this is working again, okay? Because it is weird to wrap your mind around, and you get to assume that this is going to work. It's going to correctly compute m to the n minus 1 as long as you build up the final answer correctly. All right, here's the stack diagram for pow of 2, 4. Okay, so main calls pow of 2, 4. Really, like you'd have m being 2 and n being 4, but I'm just going to draw it lazily. Pow of 2, 4. And pow of 2, 4, well, it's going to multiply 2 by 2 to the 3. It's going to call itself again. Oops, sorry. Pow of 2 to the 3, yeah? Which is then going to calculate pow 2 squared. Which is then going to calculate 2 to the first power. Which is then going to calculate 2 to the 0th power so that it can multiply it by 2. It's always waiting to multiply it by the m, which is 2 in all these cases. And then finally the base case, m to the 0, 2 to the 0, will give back 1. So this guy's finally like, okay, give back 1. And pow 2, 1 was waiting right here to multiply its 2, which was m, by 2 to the 0. It just got the answer back from the base case. These are a bunch of different calls to the same function, each waiting on each other. Okay? So it's going to return back its 2 times its 1. It's going to return back its 2 times its 2 that it got back from 2 to the 1. This is now 2 squared, or 4. It's going to multiply pow 2 to the 3. It's going to multiply its 2 by whatever 2 squared was, which makes 8, which correctly computes 2 to the 3. And then pow of 2, 4 was waiting on pow of 2, 3 so that it can multiply, once it got the answer back, it can multiply it by its 2, and we finally get 16 given back to main. All these guys go away, and now we're back in main and we output 16. Okay? That's the stack diagram. Hopefully that is making slightly more sense with a new example. Okay? It's definitely hard, I know. It's hard to wrap your mind around. This with the pointers chapter is, these are the 2 hardest chapters in the book, without a doubt. Okay? But we're making it work, all right? The next thing I want to talk about is how you can have problems with your recursive solution. So you can have infinite loops just as easily, because you're kind of looping. You're going through some numbers. You can have an equivalent of an infinite loop with recursion. And when you have an infinite loop in a recursive solution, you end up with what's called a stack overflow. So now you know why that website that you're probably using when you Google questions, now you know why it's called this. That's a fun trivia thing. So yeah, stack overflow is when your stack gets so big that you run out of memory, because you're trying to call functions within functions, and that all takes up space, right? You have the your code was, you have the heap. It's going down, and the stack is going up in some sense. And so when you call more functions, you're eventually going to cross with the heap. You're going to run out of memory, okay, with the more functions that you call. All right? and that's unfortunate. But that's what's going to cause you to become out of memory, which is a stack overflow, which will stop the program, okay? So yeah, the idea is that each stack frame, each function call, also called a stack frame, it takes up memory because it needs to store like all the little parameters and like where to return to, like, oh, I got to return to myself, or oh, I got to return to main. Okay, that all takes memory. All that stuff takes memory. Yeah. The easiest way to cause a stack overflow is to forget a base case in your program, okay? Because then it would never stop. It'd be like, okay, 2 to the 0, that's 2 times 2 to the negative 1. It's 2 times 2 to the negative 2, yeah? And that would just never stop, yeah? Base cases are your stopping conditions, and so that's an easy way to cause a stack overflow. So, yeah. Let me show you that one. So let me get rid of the base case and just only have the recursive case. There we go. This I need to say this for a second, I think. Otherwise my computer will crash. This virtual machine will crash because it will do silly things. So let's recompile, rerun. Hopefully it's not going to crash. It's going to run out of memory because it's going to keep calling pow. Okay? I can actually print it out. Be like, cout. Calling pow of m, then a comma, space, and then an n, and then closing brace, new line. How about that? Whee! And it keeps on calling. And eventually, it gets to a stack overflow, which ends up trying to access memory that it doesn't own, and that's why it's another seg fault. Okay? So it looked like it got that far. So the stack got pretty big, but eventually it ran out of room. Okay? So, sad day, but that is why that works. Okay? Oops. Let's keep all this, and let's bring all the nice stuff back. And now, a nice thing to do is, oops. You can see how it's calling everybody. It's nice to print these things sometimes. Okay, so that's pow. Oops. Whee. If only it let me go over here. Yeah, that's one way to have a bad time. Introduce a stack overflow. The other way to do it is to have a recursive case that does not make progress towards the base case, because eventually you need to get to the smaller answer that you can then give back and build up the final answer from there. If you just don't make any progress, like in the recursive case, like if you say return, if I go back to that program, if you just say return fact of n instead of this, that doesn't make any progress because n's not getting smaller. It's going to be like, okay, what's fact of n? Well, it's just fact of n. What's fact of n? Oh, it's just fact of n. And so it'll just keep calling itself forever with the same argument. That's unfortunate. And that's another way to cause a stack overflow. Okay, it's like saying, oh yeah, n factorial, that's just n factorial. Okay, and that'll cause the stack to just grow until the end of time, and that's no fun. You need to always make progress towards the base case, okay? Because that's eventually the place where you can stop the recursion and start giving back answers, start building up the answers. Okay, so fun stuff, fun stuff. The next example that I want to show you is called the Fibonacci function. You may have heard of the Fibonacci sequence. If not, don't worry, I'm about to explain it. So it's just a fun little sequence that comes up in nature a whole lot. If you've heard of like phi, the golden ratio, that's what the Fibonacci sequence is converging towards. It's converging towards phi, the ratio, at least of the two numbers right next to each other. That's what the Fibonacci sequence converges towards. So it's just a sequence, it's just a bunch of numbers, but they're defined in a special way. Okay, this is the Fibonacci sequence goes 0, 1, 1, 2, 3, 5, 8, 13, 21. And do you see the pattern? How is it coming up with this number from the rest of the sequence? Because there is a pattern. The idea is the next element, if I write it over here, 0, 1, 1, 2, 3, 5, 8, 13, 21, ... The first two numbers we say are 0 and 1. Those are like the base cases. And then every number after that is the sum of the two previous ones. So let's take that one, sum them together, yeah? So 0 plus 1, it's 1. And then this 2 is, okay, it's 1 plus 1. Add them together, get 2, yeah? And then the 3 is, okay, that's 1 plus 2, yeah, that's 3. And you can make this on and on and on forever, like the 21, yeah, that's 8 plus 13, okay? And so that's how you make the next element of the sequence. It's just the sum of the two previous elements. Okay, so that's the Fibonacci sequence, now you know. And we can make a recursive function to calculate the nth Fibonacci number. Like, let's say that this is the 0th Fibonacci number, this is the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th. So that's the order, or kind of the index into the sequence. We can make a recursive function to calculate this, because it's defined kind of recursively in terms of smaller elements of the sequence. See that? Isn't that fun? So, yeah, let's do this. So you need two base cases, because you have to start 0 and 1 off this way. But let's do the recursive case first. Like, we're trying to solve for the Fibonacci number of n, like the nth Fibonacci number, so maybe it's 6. Let's do the 6th Fibonacci number. So this is equal to this Fibonacci number plus this Fibonacci number, the 4th and the 5th. You see that? So the 6th is equal to the 5th plus the 4th. So it's equal to fib of n minus 1, you see that? Plus fib of n minus 2. That's how you can generate the next one, the nth one, from the two previous. You see how that's a recursive answer? It's using a smaller term in the sequence. Okay? And then the base case, it turns out that you need two of them, because you can't use this with the recursive rule. You can't make fib 1 with the recursive rule, because it will be like, oh yeah, that's fib of 0, because it's n minus 1, plus fib of negative 1. There is no negative 1 term. Okay, you don't go this way in the Fibonacci sequence. So that's why you need two base cases. Everybody after 0 and 1, those make sense. Those totally make sense. So from here on, you can use the two previous ones, because there are two previous ones. But for the first two, you need two base cases. Plural. So fib of 0 is 0, and fib of 1 equals 1. Okay? And so you need two base cases, and also a new weird thing, which is kind of natural because we came up with the answer. It's you're making two recursive calls here. You see that? You're calling the function, you're calculating the Fibonacci term, you're calculating two different ones. Two different smaller ones. You see that? So you need two recursive calls in the recursive case. And isn't that weird? So let me show you that. Fib.cpp. So int fib int n. So return the nth Fibonacci number. Fib of, I don't know, 7. So we have the base case, but we have two of them. If n equals 0 or n equals 1, two base cases. Okay, return 0/1. So really, I guess I need two if statements, otherwise you can't really separate it. Okay? So, yeah. Base case 1, n is 0. The answer is 0. The 0th term is 0. Else, if n is 1, base case 2, the 1th term, I guess, is 1. Else, return fib of n minus 1 plus fib of n minus 2. That's the final recursive case. Okay, you see how I'm just reading this off from what we discovered over here? That's all. And so this should hopefully give back 13. Hey, so we got 13. And that is the answer. So That's not too bad, I hope. One thing that I do want to say, though, is this recursive implementation is horrible. Okay, I'm going to show you why next time, but this is a horrible, horrible thing that we just did. These two recursive calls, they take up so much space, and they don't really, but they do so much work, okay? So much work, and it's getting repeated. So I'm going to come back next time, and I'm going to show you why this was a bad implementation, sadly. The other recursive functions that we wrote didn't have the same problem, but Fibonacci has a problem, okay? And I will show it to you. Are you ready? So I think that's all for this lecture, and I will come back and see you in the next one.